Hey guys, I'm going to be sharing with you guys the multi-sim that needs to be built to complete this activity. And I realize that some of you guys don't have multi-sim or multi-sim live, and I'm going to share with you the build circuit, and I will go ahead and manipulate it. That way you can play it, rewind it as many times as you need, so that you can extract the information you need to answer the questions and to complete the activity. So starting in this unit, where we should be using the breadboards with S6 or S7 chips, which those are the really long ones that we took off in the beginning of the year. I don't know if you guys remember, but there were these really long chips that we took off, and those require multi-sim, the multi-sim program, but a different packet that the program has. We have been using the multi-sim just to do the schematics, the circuits on there, but we can also use them to create circuits and send them to that chip. So remember, that chip takes care of a lot of the AOI that is used. So instead of us having to like, let's say when we did the majority vote, we designed it on multi-sim, we put the buttons, and then when we built it on the breadboard, we had to put each AOI that we needed. And remember, each chip had four of the AOI components in there. So that there was 4 OR gates, 4 AND gates, 4 inverters, or whatnot. But with the PLD mode, which is that packet I'm talking to you about in the in multi-sim, you create the circuit the way you did it for the majority vote, but then you send that circuit to the chip, and on the chip all you would have to do is just push the buttons that are on there for the voting. So you no longer need to breadboard each individual chip to create the majority vote. So that's one of the major components from starting from Unit 3 that we will not be taking advantage of. So everything that we do from now on is going to be on multi-sim, just a regular multi-sim. So when it says something like PLD mode, we're not going to be doing that. All right, and you'll see how the buttons look different on the pictures if you've been looking at the activities. So I'm cutting off that stuff, but just in case I miss something, if it says anything about PLD or S6 or S7 chips, we're not doing that in class. Okay, so this activity is 3.1.3. This is a flip-flop application with shift registers. So what is a shift register? Well, a shift register is going to be using the flip-flops. So a shift register uses flip-flops, and it literally shifts the information from one flip-flop to the other. So, for example, in this JK, right? In this JK flip-flop, whenever Q is 1, then it's going to send it over here to J. And then whenever Q is 1 over here, it's going to send it to this J. But in order for it to go from this one to this one to this one, well, we first need to activate the first flip-flop. So once you activate the first flip-flop, it stores the data, and then once it toggles, it's going to create the data for the next flip-flop. And it's going to be shifting from one flip-flop to the other. That's what a shift register does. We're using the flip-flops to store information, and then we're going to use this circuit, right, as a path to go from beginning to the end, from the first flip-flop to the last flip-flop. So you're going to be designing this on multi-sim. Of course, it's always better for you to do it so you can play around with it. So once we design this, you're gonna come down here. Okay, so once it's designed, I'm just gonna go ahead and toggle the D and C buttons so that we get, so you can observe what's happening with the count. Notice here that it says, let's see here. Notice here it says the least significant bit, and over here it's the most significant bit. So the number is written from, like this represents 2 to the power of 0, 2 to the power of 1. So let me just write that down real quick. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 3. So like let's say you wanted to display the number 2, then it's going to be 0, 1, 0, 0, and over here it would show you a 2. If you wanted to display something different, like let's say, I think in the example it's asking you to do 1, 1, 0, 1, so 1, 1, 0, 1, so that's going to be 1 plus 2 plus 8, so it's going to be 11. So remember, when you have a hex display, you go 9, then you got 10, then you got 11. So 11 was B. And all the way, you got C was 12, D was 13, E was 14, F was 15, and that was the largest one. Because once you get to 16, and you can divide 16 by 16, so that means you go back down to the least significant bit. All right, so this is what this is. This is a counter. So let's go ahead and let me go ahead and do that for y'all, for you guys that don't have multi-sim. All right, so I'm starting the simulation, and then I'm going to start toggling the buttons. We got C, so that's 15, and then D. I'm going to go C again and D again. And I'm just going to keep toggling here. Now we have 14, right? So there we have 1, 0, 1, 1, which is the one that we were asked to look at and how it activated down here on the Z. This is the one that they're asking. So our circuit does work. All right, so this is number 15. And then it says here, so I mean I can keep toggling here. And it says here, make the necessary, number 3, the modification to the circuit, so it will detect the input sequence 0, 1, 1, 0, simulate this new circuit, and verify that it is working. All right. So for it to detect 0, 1, 1, 0, which is this question right here, question number 3. We wanted to detect this. That means we have to play around with this guy right here. This is the one. Like we need to, whenever this is present, we need to wire this to read that. And if it reads 0, 1, 1, 0, then we go ahead and we have a recognition of this number, which would be, this would be 2, and so the number 6. So I want you to recognize the number 6. So then what's that going to look like? Like you would literally need multi-sim because you'd have to play around with this to make it work. All right. So this is what it would look like. So notice what is the main difference here. The main difference is following. So this is what I want you to do, is just pretty much just compare, right, where these inputs are coming from. All right, compare where these inputs are coming from, and then later on we're going to be using a 4 input AND gate as opposed to using 2 and 2 and then taking it to 1. So just a 4 input AND gate is going to make life a whole lot easier. So so just observe what is happening with these inputs, where they're coming from the circuit, and if you can just describe that when you turn this in, then you'll get credit for this. If you can take screenshots of either my simulation or your simulation, just to kind of just verify that you went over the activity when you turn this in. All right, I'll talk to you guys later.